So I guess you all know the title of this day will be 4 sessions about seeing how to use OpenFOAM to do some multiphase flow and evaporating flow simulations, essentially boiling, let's say. I've worked mostly with boiling in the past, boiling and condensation. This is not working to change slides. So first of all, who am I? This is a question I ask continuously to myself, but at least these are the main point which brings me to which are my track toward this day. I got my PhD in energy engineering in 2012 in Italy. I did a long postdoc at the PFL in Switzerland, but I was not satisfied by doing only one postdoc, so I did also another one at Imperial College. In between, in 2015, I started using OpenFOAM, and I never stopped until now. And since 2019, I'm assistant and then associate professor at the University of Nottingham. So I've been moving around quite a lot. I also had many research visits during all these years between Princeton, Tel Aviv, and University of Maryland because I was getting really bored during my years in Switzerland. And a bit of my more recent research activity. So I have just 6 text boxes here. The top left is about flow boiling in microchannels, which is what has driven my research over the past 10 years, I would say. And this is a simulation of a bubble boiling in a small channel, everything done with OpenFOAM using the solver I will introduce today. Second box here in the middle is static. There is no motion, but this is a work that I'm currently doing on buoyancy effect in two-phase microfluidics, and this is actually work that I'm using Basilisk for it. And it's the only work in which I started using Basilisk in the recent years. And on the top right, we have an ongoing work with no phase change, but it's pure fluid dynamics to understand the fluctuations, the oscillations of the tail of bubbles in small channels. So here we are talking of millimetric channels. So still kind of microfluidics, which is what I've been working on for many years, but with no phase change in that case. Bottom left, this should be a video. No, it's not. It's a static image, bottom left. This is a work I've been doing with a PhD student who just graduated this year, which is about, instead of having straight microchannels, let's have channels in between pillars. So I forgot to introduce the fact that on the top left here, we are talking about micro evaporators. So miniaturized heat sinks of this size, let's say 1 centimeter by 1 centimeter, or as much as you need to cover a CPU. And in this 1 by 1 centimeter, you may arrange many straight channels in parallel, which is, let's say, the top left here is a unit of those channels. Or instead of having segregated channels running in parallel, you can have the walls of these channels replaced by pillars, so that the fluid can actually move in between pillars, which is supposed to improve the uniformity and the distribution of the flow. And with a PhD student, we have been using OpenFOAM to simulate these kind of flows and see what's the heat transfer, the pressure drop, how they compare to straight channels. Bottom center is something else I started working recently, which is about, instead of having bubbles confined within channels, these are very traditional pool boiling bubbles, like what you would see in a tea kettle, where you have a pool of liquid which is stagnant, and you have bubbles that start growing on the bottom surface where the nucleate. So here we are specifically interested in that very thin layer of liquid that remains trapped between the bubble and the wall, which is invisible when you look at the full scale. But if you could zoom in under the bubble, you would see that there is a micrometer size film, whereas the bubble reaches millimeter sizes. So we are talking of a 1/1000 scale difference. That's why you don't see it. Something else on the top right, this is pure madness. I don't know if it's ever going to work or everyone is going to use it. But this is about using molecular dynamics and CFD in the same simulation. So the problem of boiling is that you can never capture it at a continuum scale. A bubble nucleates because of some molecular interactions between the fluid and the surface when the surface is hot enough. So you can use OpenFOAM, you can use Basilisk, you can use the most sophisticated CFD software ever, but you always need to see the bubble. The bubble will never be born naturally if you use traditional Navier-Stokes equations. To have the birth of that bubble, you need to be able to capture somehow the statistical fluctuations that give rise to the birth of the bubble. So molecular dynamics is actually the most fundamental, let's say, modeling principle that allows to see the birth of the bubble. But molecular dynamics is restricted to some nanometer scales. So you can never bring it up to real useful scales. So what we are trying to do is to breach this limitation by having molecular dynamics limited only near the wall, so to limit the computational cost. But that's fine for us because we care about the molecular effects near the wall. Molecular dynamics will handle nucleation, will handle the contact line, and the CFD solver is placed above the wall, and we get the molecular dynamics field as boundary conditions, which is what you see here. This is a one-way coupling, so molecular dynamics is evolving agnostic of CFD, but we have achieved part of the two-way coupling without the bubble, so having, for example, a Couette flow, single phase. We have achieved two-way coupling. In that case, the CFD is also providing a constraint to the molecule to the motion of the molecules, so that MD and CFD, they actually interact. Here is still a kind of one-way coupling, but this is something we are trying. We have submitted at least 5-6 proposals on this topic. It has been accepted only once by Archer 2, which is the national supercomputer of the UK. They don't care about bubbles, they care about merging the two softwares, so that's why they funded us. If you have some savings to spare, please, I'm going to give you my project code at the university. So let's say that this is what I've been doing in the past, let's say, 2-3 years, and the topic of the course today is about how to use OpenFOAM, which would allow you to do the simulations that you see top right, top left, bottom center, and this solver here is actually, we put it on GitHub. We have a publication about it, we put it on GitHub. It uses OpenFOAM for the CFD, and it uses an in-house molecular dynamics solver for the molecular part. So, format of the day, I thought of having the more structured classes in the morning, starting with an introduction to OpenFOAM and the multiphase models in the first hour or so. We will probably enter a bit also in the second session. But the second session, I want to delve into modeling evaporating flows with OpenFOAM. And then I'm leaving the afternoon for the hands-on sessions where there are some tutorials that I have prepared. Meantime, during the first 2 hours, I will still go into the virtual machine to show you some things. So it will be hopefully a bit of an interactive session, not just me talking for a couple of hours. Please feel free to interrupt me at any time. I want this to be, a two-way interaction all along the day. So this was just a brief introduction slideshow, and I'm going to move to these slides here that you should have been, so we have shared with you a link where you could download the entire virtual machine. So what is going on here? Why do we have this? So I'm part of this kind of, it's called Virtual Institute of Two-Phase Flow and Heat Transfer, where the members, they share data, they share software, and it's a big consortium with many labs working on multiphase flow and heat transfer. And I personally curated this educational tools page where I have uploaded my own OpenFOAM training for beginners. I've done this because for many years, I think for 4 years, I've been having yearly workshops where I was teaching OpenFOAM for a week. So I thought that instead of having random material every year, I started to put together all my material in a kind of coherent way. Then recently I started to have some weekly teaching of OpenFOAM also in other universities, so I decided to create this slide pack, and especially to create a virtual machine where everything is inside. So if any of you has been able to follow the instructions here, I have provided an Ubuntu virtual machine that needs Oracle VirtualBox to be installed. Unfortunately, it doesn't seem to work with the new versions of Mac. But let's say that if you're able to install the virtual machine that has already OpenFOAM installed inside with everything needed, then you can use a set of tutorials that I have prepared. They are called OF Training, the name of the folder. And you can follow OF Training slideshow to do the entire tutorial. Now, this is a big tutorial planned for 5 days, from zero to boiling. Today, I'm trying to get a bit of an accelerated version of it, where we are going to do only, let's say, part of the tutorial. So I'm still going to go through the entire slideshow of the tutorial, but I will just pick the necessary bits. So specifically, this tutorial is divided in days, and I will just take introduction to OpenFOAM from day 1. I will leave Laplacian form, which is heat conduction with OpenFOAM. I will leave single phase flow with OpenFOAM. I will go straight to day 3, where we have simulation of multi-phase flows. So this is what we are going to end in this first session in the morning, in the first hour. I will skip day 4, which is some extra functionalities with OpenFOAM to do some runtime processing, automatized submissions of simulations, and so on, and go straight in the second session of this morning to phase change and boiling foam. Boiling foam is my own solver to do boiling simulations with OpenFOAM. So I'll stick to the slides for a tiny bit now. And so OpenFOAM, well, OpenFOAM has been around for around 20 years as an open source toolbox to solve PDEs. That's what OpenFOAM is, essentially. It's a big C++ library to solve partial differential equations. So you have CFD equations, you have finance equations, you have also molecular dynamics solver. There are, think of OpenFOAM as a solver of PDEs in general. Then there are pre-compiled solvers that, like a solver for single phase incompressible flow will put together the solution of the equations of Navier-Stokes, so momentum and pressure equation. So there are all the libraries to solve different kind of equations, and the solvers, they put together these libraries to achieve a certain kind of flow field. And so, you need to know the physical problem you want to solve to decide which solver to use, which equations to solve. There is no graphical interface, so everything is assembled by putting together some TXT files. There are 3 main distributions of OpenFOAM, and I'm going to use the first one, ESI OpenCFD release, even though for the basic part of the tutorial of the morning, also the OpenFOAM Foundation will just work as well. They are parallel distributions with most of the solvers, they are the same, but when you get into the more sophisticated ones, then they start differing. Yeah?
Is there a web page that shows something like a clear differentiation between them, what one can do versus the other?
I'm not aware of it.
Like a compatibility matrix
Yeah.
type of thing.
I'm not aware of that, unless someone has done it just for the sake of clarity. I think it's mostly that if you need the basic single phase solvers, they're absolutely the same. When you start getting into, for example, multiphase flow, the version I'm using has invested many years ago in a geometric volume of fluid method. Whereas the OpenFOAM Foundation, it implemented it only in the past couple of years. And for the first version, there is also a newer library, not in the official release, but it's a big library that has all different geometric VOF and different methods to implement surface tension, including height function and all the most recent ones. So my own feeling is that if someone is interested into multi-phase flows especially with strong surface tension effect. The ESI OpenCFD release is a bit better. The second one seems to be interested in, they developed further some other kind of solvers other than the multiphase flow solvers that are better developed, to my opinion, in the first release. Thanks, Radu, for the question. I keep trying to switch slides with this one. Main features of OpenFOAM is written in C++. Operators are defined for top-level programmation. So we will see later when we sneak into the solvers that you can solve new equations just by calling the different component terms of an equation. And the different terms will be discretized with the already available libraries to discretize a convective term in different ways. So you don't need every time to reinvent the wheel if you want to implement a new equation. Complete access to the source code is based on finite volume discretization. Many solvers capable of parallel computing, but not as much efficient as Basilisk, I should say, about parallel computing, because Basilisk is reallocating the cells to different processors to make sure that every processor more or less has the same number of cells. It's called load balancing. So every processor is efficient in the same way. Unfortunately, in the native version of OpenFOAM, this is not happening. So if you have a big domain and one bubble moving around, different parts of that domain will have the bubble with many cells, but the distribution of workload between the processors will depend on time step 0. So if at the beginning the bubble is at the center and you have all the processors split in the bubble, everything works fine. But if the bubble starts moving around, some processors will have almost no cells. Some processors will have many, many cells. Those processors are going to kill a bit the efficiency of your simulation. There are libraries to implement load balancing. They're available online. I tried them. Sometimes they work, sometimes they crash. I think you need to personalize them a little bit for the architecture of the supercomputer you're using. On the other hand, OpenFOAM is capable of unstructured and unstructured meshes, polyhedral cells. It does adaptive meshes. It has a very large online community. So if you need a solver that is not available in the native version, you may find something very similar to what you need online if you start Googling for it. It has a growing documentation with user guide, tutorial guide, extended code guide, programmer's guide, and so on. Constant development is released every 6 months in both distributions of OpenFOAM. Now, your OpenFOAM installation, here I'm talking of the one that is in the virtual machine. So the virtual machine I have prepared, it uses Light Ubuntu version 20, and it has OpenFOAM 2106 and ParaView installed. So in the distribution of OpenFOAM that I'm using, 21 means the year of release, 06 means the month. So OpenFOAM is released every 6 months. You will find 2106, 2112, 2206, 2212, and so on. The 2406, which is June 2024, has just been released last week. Now, I'm using 2106 mostly because I'm lazy. I don't want to every 6 months update the tutorial, but also because the solvers I have personalized, they were based on 2106. They still work in 2112, they still work in 2206, but I have not updated them for newer versions, so I'm sticking to 2106 for now. But the basic principles you learned today about how to use OpenFOAM are still valid. Those are always valid. It's only that the boiling foam solver we will use for the boiling simulations is not available on the newer versions. Now, if we take a look at the virtual machine, that's where I start jumping from slides to virtual machine. So what you really need to do, provided that everything works well, is to download the VM Ubuntu 20L here from this website. So if you click here, you should be able to download it. It's 5 giga, it takes some time. You install Oracle VirtualBox. So Oracle VirtualBox is a VirtualBox manager. And then if you go with the file import appliance, you simply import the .ova file you download. It takes maybe 10 minutes to install it. And before running it, so this is the virtual machine we are using, the second one on the list. Before running it, when the machine is still off, you can set up the shared folder to transfer files from your operating system to the virtual machine. So if you go to settings, shared folders, here, if you install it in your computer, you absolutely need to update the folder path to the shared folder, because otherwise it will look for the folder path in my computer where I prepare the virtual machine, which obviously will be a different path from yours. So in this laptop, I have created a shared folder. You can put it everywhere. I've put it in the desktop. This is just a folder. It's a folder that you can call it the way you want. What matters is that here you give the full folder path to the virtual machine, and everything should be really plug and play. If there is no other issues with acceleration of your graphic card, some of these issues, I know about them. If you encounter them today, I can try to troubleshoot them. I may not be able to sort out other issues. But let's say the only steps to do are to import the virtual machine, set up the shared folder, and once you then activate the virtual machine, this is the way it looks like in my computer. And so the virtual machine, I choose Ubuntu because it looks very much like Windows eventually. So because I prepared all these tutorials also for my students at university, Ubuntu was a good operating system not to scare them too much. So you have a desktop. Ubuntu works with a shell, so I have a shell open here that we will use to do the exercises, but you can also browse all your folders manually. Now, everything looks extremely tiny. I spent £2,500 for this laptop to have a 14-core workstation. Well, when I put the virtual machine inside, it's just incredibly tiny, and I cannot fix this. So even when I want to use ParaView, all the icons are immensely small. So I'll try to do what I can to make everything bigger. For the shell, I can change the font size, but I couldn't find a way to change the size of these parts yet. So you probably cannot see this, but inside the virtual machine, there is an OpenFOAM folder. There is a user folder. In the user folder, there are only the things that we put in. The actual OpenFOAM installation is somewhere else, and I will show you now how to get there. So going back to your OpenFOAM installation, now the OpenFOAM script will not run automatically if you just turn on the virtual machine. What you need to do is to open a terminal and type OF2106. Once you type OF2106, everything is loaded. This is happening because I have set up the virtual machine to require the user to specify which version of OpenFOAM they want to open. Because you may want to have different versions of OpenFOAM in your virtual machine. So I could set it up in a way that when you open the terminal, OpenFOAM is already loaded. But I decided to have a specific line here so that if we want to use OF2106, you just type OF2106 and it will load it. You can install multiple versions of OpenFOAM. They will not clash with each other. And then you set different aliases here so that you load only the version that you want to load. Now, going back, taking a look at the slide, I can close this one. So the preparation here would be go to the shared folder, take the OF training folder that I have put, in my case in Windows, in my shared folder. So I downloaded it from the web, I put it in Windows, OF training. I put it in my shared folder, and now that it's there, the folder is available here in the shared folder section of the virtual machine. You don't necessarily need to do this. The virtual machine can also go in internet, and you can go to the same web page and download everything. What you need to do then, copy your OF training and put it into OpenFOAM user run. It doesn't really matter where you put it. OpenFOAM can be run from any folder, but I like to be tidy. So in this user folder, I have a folder called run where I put all the test cases. And I have another folder called solvers on the top right where I put all the solvers that I modify so that I try to keep everything in a tidy way. The folder called platforms is a folder of OpenFOAM where every time you compile a solver, it puts the executable there. Now, there are several, we call them macros once you have OpenFOAM loaded. So, with an OpenFOAM macro, they all have this dollar and something. You can, as a matter of fact, they point to a specific directory. So $WM_project will go in the folder where you have OpenFOAM installed, or WM project dir. So if I open a terminal, hopefully you can see this one, I enlarged it. And you do, for example, echo $WM_project_dir. You see, this is where it's pointing up. It's pointing to. So the OpenFOAM installation is actually located under user lib OpenFOAM OpenFOAM 2106. You don't need to know where they are for now. You only need to know it if you start making changes to the solvers of OpenFOAM. So now, going back a bit more in detail into the slides. This is the structure of the code. So if you type, like I did, cd wm project dir, you will enter in the installation of OpenFOAM. You will find a few main folders. Applications is the folder that has all the solvers. So if you go application solvers, you will find all the solvers of OpenFOAM organized by topic, let's say. The folder tutorials, as the name says, has all the tutorials of OpenFOAM. Then there are some extra folders like bin, I think it has the executables. Doc has some documentation that you can find also online. etc, I think it has all the bash files to load the solvers. Platform wmake, these are all for installations. There is an important folder called src, which is the folder that has all the libraries for discretization of infinite volumes, for the discretization of the terms of an equation, turbulence transport models. So let's say that under src you find all the libraries. Under solvers, every solver will call specific libraries depending on what kind of PDEs is the solver solving. So for example, the solver for the volume of fluid method doesn't have the libraries for the volume of fluid method inside. The libraries for the volume of fluid method are under src, and the solver will call them specifically so that different solvers can call the same libraries. So that's the way the code is structured. And here, this is a probably not exhaustive list of all the solvers you have in this version of OpenFOAM with a brief description of them. Now, today we will only use interFOAM and interisoFOAM. interFOAM is a multi-phase flow solver based on an algebraic volume of fluid method. Algebraic because it doesn't reconstruct the interface like, for example, Basilisk is doing. More about this later. InterisoFOAM is the newer version of the VOF, which actually has a geometric VOF solver to reconstruct the interface. So we will work mostly with with Interfoam today and maybe a bit with InterIsofoam if you try to do the exercises I propose. Now, OpenFOAM comes with pre-processing utilities where you can make simple meshes on cubic or rectangular square domains, but you can actually import more complex geometries, for example, to study flow around a car or whatever you want, and you would use Snappy Hex Mesh, which is a bit of a more sophisticated mesher for OpenFOAM. You can also make your mesh somewhere else, for example, with Salome, and import it. These are all the solvers. For post-processing, OpenFOAM natively uses ParaView. So there is a ParaView installation in the virtual machine I provide. I always use ParaView for visualization. You can, of course, sample data over lines, over surfaces, and extract them and load them with Python or MATLAB, which is what I'm using. You can, of course, convert your OpenFOAM result into a format that is, for example, possible to open it in TechPlot or even in ANSYS if you want. Okay, now let's get a bit into more details of OpenFOAM discretization now. I'm assuming that you are all familiar with the basic principles of PDEs, discretization, so we'll just recall the main aspects here. So OpenFOAM exploits the fact that all partial differential equations in fluid mechanics can be somehow recast in the same form. So if you take the continuity, momentum, and energy equation for a single phase flow, you will see that they all have the same terms. There is a temporal term, a convective term, a diffusion term that is 0 in the mass equation. There is a source term, which in the momentum equation is pressure gradient and gravity term. In the energy equation is any source of heat that you may have. So all the equations can be actually written in the same general manner and discretized with a finite volume method, or at least integrated in volume, switching the volume integral into a space integral. So you have a very general equation that is the same for all equations. So if you develop a method to discretize the convective term, this is applicable to all of them. It may work better or worse depending on the specific properties you're solving, but you can actually develop a discretization method and call it in OpenFOAM with its own name that you define. So if you want to solve 3 equations with a new discretization method you create, you don't need to discretize it in each equation. You make a library for it, and then you call it up. Now, it is useful to know that this general equation here has a specific syntax in OpenFOAM. So that equation there is solved by OpenFOAM by typing d dt of A, temporal derivative of A. A can be rho u when you have the momentum, it can be rho Cp t and you have energy, it can be rho and you have continuity equation. Divergence of phi of A, so phi in OpenFOAM, you will see it around. Phi is the volumetric flux across a control volume phase. So it's the scalar product of speed on the phase times surface normal vector. So phi is the flux, A is the variable for which you are solving, minus, I'm bringing this term on the left-hand side, Laplacian of dA, A. dA is the diffusion constant, gamma. A is the variable you're solving for, equal FV options. FV options is OpenFOAM nomenclature for a source term. So FV option of A, you will have another somewhere else in the code where you define your source term, which typically in the finite volume method or in any linear solver will be of the kind source equal to an explicit part plus an implicit part, so that you can solve it with a linear solver. So you can simply, when you take a solver of OpenFOAM, if you add a new line and you simply include this, providing boundary conditions and initial conditions for A, providing the A, you have a new solver that solves a new equation, as I will show you. So it's very simple to solve new equations in OpenFOAM, provided that you don't need some complicated divergence schemes, provided that you can use the divergence schemes that are already there. So for temporal discretization, when you will set up your simulation, you have to tell OpenFOAM, well, which discretization scheme to use for DDT. So we will see that somewhere in OpenFOAM we have the chance to choose DDT schemes, and OpenFOAM just uses very standard temporal schemes that are first order implicit, first order explicit, second order Crank-Nicholson. But you can choose them by giving the right name in your tutorial folder, in your case setup folder. I'm not going to go more into the details of this part. We will see the details later when we open a tutorial file. Divergence schemes, OpenFOAM discretizes it in a very traditional way by turning the integral into a summation of the fluxes over the faces. And summation of the fluxes over the faces needs interpolations from cell centers to cell faces. So we need to tell OpenFOAM, for example, the value of the variable you are solving for. How should OpenFOAM get it in the faces of the control volume? So for the divergence scheme, you will choose div schemes. And for example, Gauss linear is a specific nomenclature that will use the traditional linear scheme to interpolate from cell centers to the cell faces. And this is all the possible discretization schemes that you have for the convective term. The linear one, we know it works well only when you have a Peclet number of the flow, which is very small, otherwise becomes unbounded. So you may choose to use upwind, which is a first order upwind. Linear upwind is second order upwind. TVD schemes, which are a bit more accurate and bounded compared to the previous ones. So you have many that you can choose. If you know the kind of problem you're solving, then you know which solver may work better for you. Laplacian scheme, so this is for the diffusion term. The diffusion term, again, like the convective term, is discretized as a sum over the control volume faces. And in the control volume faces, you need to know the diffusion constant and the gradient of the variable evaluated on the face of the cell. So in OpenFOAM, you will have Laplacian schemes, Gauss, and different schemes for calculating the, let's say, interpolation scheme is how you want to calculate the diffusion constant on the face. Surface normal grad scheme is how you want to calculate this scalar product here, which is the gradient of the function on the face of the cell, times the surface normal vector to that face. So the interpolation schemes are the same that you have seen before, the same as those of the convective term. For what concerns the surface normal grad schemes, you have a few here available. Here I'm showing, for example, in the orthogonal case, things are a bit easier. If it's a non-orthogonal mesh, then you should use some corrected schemes that take into account the fact that the mesh is not orthogonal. Now, once you discretize all the equations, you know that your generic PDE is turned into a linear system of equations, and you can write it in a matricial form this way. Your linear system of equations will have n times n, will be a big square, will form a big square matrix. N is the number of cells, and you need to tell OpenFOAM which linear solver to use. If you want to use a preconditioner or a smoother, which are these techniques to solve a linear system in a faster way. Of course, OpenFOAM solves everything iteratively, so all the linear systems are solved with iterations, and you need to tell OpenFOAM when to stop the iterative procedure. So another input you need to give when you want to set up a problem case is OpenFOAM calculates the relative residuals, so how far you are from solving the linear system perfectly. So the residuals are an indication of how much this is not true. So you bring B on the left-hand side, everything should be equal to 0. If it's not, that's the error you're committing, that's called residual. They are rescaled so that they are non-dimensional and they are independent of the scale of the problem. And you have two indications you can give. An absolute tolerance, for example, 10 power minus 6, typical tolerance we use in OpenFOAM, or a relative tolerance relative to the first iteration. So you may say that, well, you know, for example, the pressure equation, I'm going to solve it multiple times because I'm using a predictor-corrector approach. So I don't need every time to go to 10 power minus 6 during the initial corrector steps. You can choose that, well, just go 100 times smaller than the residuals you have at iteration 1, and that will be enough. So you can choose, you can set both, and OpenFOAM will stop the simulation, I think, when the first of the two is satisfied. You can put rel_tol to 0, and it will only look at the tolerance residual threshold, the absolute tolerance. So I want to show you first how a solver in OpenFOAM looks like. So this is a simple solver. It's Laplacian form. Laplacian sum solves the temperature equation for heat conduction. So temporal term, diffusion term, there is no convection here, source term. So if you open the solver, for example, we can do it from here as VI $, or I can just do it by hand and go in user, no, I should go more up. I think that the installation is under, is it under opt? No. Under user, lib, OpenFOAM. So this is the, it's very tiny, I'm sorry about it, but this is the structure of the folders I showed you before. You go to applications, solvers, basic, Laplacian form. So hopefully this will be a bit bigger. Open with feather pad. So this is how a typical solver of OpenFOAM looks like. I'll try to zoom in a little bit. On the top, you are calling some very standard libraries that are called in every solver. OpenFOAM is a C++ solver, so you can also create a solver to just tell you hello world every time you run the solver. The typical, you know, first exercise you do with programming in C or C++. Now, let me skip all these include here. Here it's including all the libraries necessary for the basic finite volume solution of the problem, so they will always be there. I just want to focus on this part here, which is the solution of the temperature equation. So you see, here we have finite volume method, temporal derivative of temperature minus Laplacian of temperature equal to the source term. So this is the bit where you're solving the temperature equation. If you want your solver to solve also another equation, you can simply add another line just the same as this one, provided that somewhere you define the variables. So what will be the name of your new variable, what will be the name of the new diffusion constant, but it's just as simple as that to solve new equations with OpenFOAM. You can simply create your own solver by adding lines to the existing ones. You see, once you type ddt of temperature, you don't need to say in the solver which temporal discretization scheme to use. You can do that when you set up a case to use this solver, for example, to calculate the temperature on a square. It's when you set up your case file that then you will say, well, use one of those discretization schemes I told you before, for example, Euler. And OpenFOAM knows that Euler is a first-order implicit scheme. So you don't need to code all these things. That's what we call top-level programmation in OpenFOAM. It has already all these dictionary inside. You don't need to go into the very details of the new equations you want to solve. You just need to kind of write up your equation there using OpenFOAM syntax. And we will go into the details of the tutorials later, but a typical tutorial case of OpenFOAM has a tree structure where you have the folder where you put your everything for your exercise. Then you always have three folders: a zero, a constant, a system. Now, zero is the folder where you put all your initial and boundary conditions. So within this folder called zero, you will have one file for each equation you want to solve. So in the case of Laplacian form, it's just solving the heat conduction equation. So there will be only one file named t, because t is the variable you're solving for. In that file, you will provide initial and boundary conditions. In constant, the only thing you need to put in is a file called, well, it depends on the solver, but there is a file called the transport properties, where you need to put in rho of the liquid, rho of the gas, mu, surface tension, and so on. So transport properties is always the file where you put the physical parameters of the problem. Under system, under system is the manager of the simulation, of the solver. So there will be a finite volume schemes file where you provide all the discretization scheme for all the terms of the equations you're solving. There will be a file called FV solution where you provide all the details of the linear solvers. And there will be a file called control dict, which is the management of the simulation. How many time steps, what's the time step, how often to save, which format to save your data, which runtime processing you want to do. Everything will go in control dict. I forgot to mention block mesh dict, which is about making the mesh. So the mesh will be done using a file called block mesh dict, where you provide the position of the vertices, how many cells in one direction, how many cells in the other directions, if you want to have any grading, if you want to have any arcs connecting points instead of having straight lines. Everything goes in block mesh dict file. Once the mesh is created, all the information about the mesh go into this polymesh folder, which is created by OpenFOAM. Polymesh will have all the information about position of the nodes. You don't need to care about it. It's ParaView who will read what's under polymesh to show you the mesh on the visualization. I will go through each file later when we start doing the tutorials. Do we have any questions so far? I acknowledge it's a bit all in a rush, but this is really to get the principles.
I've got one, but it might just be a C question.
No, go ahead.
On the previous slide, when you were saying you can add more equations,
Yeah.
how would you do that? Would you have to like leave a line between them? Because you still cross the lines there with that one equation.
So TAQN solve is where you are actually solving it. Here it's simply preparing the matrix. Yeah. And so what you can do is I would simply copy-paste this block underneath. And it will solve in sequence this equation here and afterwards the next equation. Then it depends if the second equation depends on the first. So you may want to have the second solved after the first. But if I got your question, it's as simple as that.
Colored square block there.
Yeah, no, the red block, I put it in. Yeah, it's just to show you.
Yeah, no, sorry, I mean, but everything in the block you need.
Yeah, not only everything in the block, you have also these three elements here that you will need to copy paste. Any other question?
Yeah, and a question, maybe I missed this block of information. You told earlier about some external programs for their machine.
Yeah.
And could you please advise us which one? Because it's quite a difficult task, I think, to implement the external machine to the...
It is. I'm not going to go into those details today, but you need to have your STL file generated somewhere. You know what is an STL file? You know, like the surface with all the dots. And then you need to use, there are a set of tools. You need to create a big block, which is like bigger than that shape, let's say. And then OpenFOAM will subtract that block. Let's say you want to study an external flow. OpenFOAM will subtract that block from the mesh you have created and adapt all the cells close to the surface so that they are clipped in the right way.
So this is a special tool for adapting?
Yeah. It's inside OpenFOAM. We can talk about it. And everything is in these slides. I'm not going to cover it, but there is a specific exercise about that. You're welcome. Anything else? Okay, I would now move forward to the multiphase flow part. So in my slides here we are talking of day 3, simulation of multiphase flow using interfoam and interisofoam. So these are two different solvers for OpenFOAM. Interfoam is a geometric WOF, interfoam is an algebraic WOF, interisofoam is a geometric one. And this is the first tutorial we will run in the afternoon, which is also a tutorial provided by OpenFOAM, where you have a water column here, which will fall due to gravity. And it's a typical validation case for multiphase flows, even though it's not particularly demanding for surface tension. I don't even know if surface tension here plays any role, because it's quite a big box that you are simulating. It's like 0.5 meter high box. But we're going to go now into the details of how multiphase flows are solved in OpenFOAM. So let's start with interfoam solver. Interfoam is a solver for, maybe so that you can all see, I can stay here and use the laser pointer. I guess at this point, after Radu's talk yesterday, you're all familiar with the volume of fluid method, even though interfoam is an algebraic WOF solver, so it's less accurate than the geometric WOF, but it has some advantages, as I will say. Interfoam is a solver for two incompressible immiscible phases using WOF. So it solves the transport of the volume fraction equation, where the volume fraction is the fraction of fluid 1 over the volume of the cell. So 1 where a cell is filled with fluid 1, 0 in a cell filled with fluid 2, values in between in a cell where both fluids are inside. Compared to the WOF equation you may be familiar from the lecture of yesterday, this one has an extra term here, which is called anti-diffusion term, and I will explain later on what this is about. Then we have a continuity equation, which because everything, the densities are constant, it turns into a divergence-free condition for the velocity field. The momentum equation that OpenFOAM rewrites in a slightly different way, as you see here at the bottom, but we'll not go into the details of that. But essentially, OpenFOAM rewrites the pressure by removing the hydrostatic component. And so these are the equations solved by interfoam. If you open the solver, you will see these equations, but they're a bit more difficult to actually to notice, because it's a pressure correction, pressure velocity coupling. So it doesn't solve the continuity equation directly, but it turns it into a Poisson equation for pressure. And now, with WOF, the big issue is the convective term. How to discretize the convective term here? Because you want to make sure that your volume fraction remains bounded between 0 and 1 and remains sharply changing from 0 to 1 across the interface. So if you use a very typical discretization method, I show it to you in one dimension, so derivatives become d over dt and d over du. The velocity in one dimension must be constant if the flow is incompressible. You integrate it in space and time, then you solve your temporal integral just as volume fraction at the new time step minus volume fraction at the old time step times cell size plus velocity is taken out of the integral, and you have the integral of alpha in time, alpha now evaluated on the faces of the cells because you have d alpha over the x in the x. So essentially you must know the flux of alpha on the faces of the cell, which, you know, if you multiply u by alpha, you get the flux. So let's say that alpha at the new time step is equal to alpha at the old time step minus the net sum of the fluxes of alpha at the two faces. So everything is quite intuitive. Imagine to have this one-dimensional domain. You are solving for this cell I here. If you know the fluxes here, you know what will be. You just do a balance of the fluxes and you get the alpha at the new time level. Now the difficulty is to get alpha here, because if you have a typical VOF where, for example, this is your interface, you understand that alpha is the ratio of colored area over the area of the cell in 2D. So alpha interpolated on this cell here may have absolutely no meaning whatsoever. So if you use this typical method here that I show in the slide, which is the way you would solve a convective term in any equation by interpolations, you would see that if you use a low-order scheme to find the interpolated value of alpha, low-order scheme, for example, finite central differences where you take alpha here minus plus alpha here and you take the average of the two, very typical second-order scheme. Well, you would see that over time you have a big diffusion of alpha. And alpha does no longer go up to 1. Your interface would smear out over time. You can use a high-order scheme, for example, a third-order scheme or higher. And what you would find is that your interface, yes, it remains sharp, but it starts having these high-order fluctuations where alpha goes above 1, below 0. And that's obviously a problem because you get fluid properties that are completely messed up, where you get densities that will be below the one of the vapor or above the one of the liquid. So these are the big issues with the volume of fluid method. You cannot use typical convective terms you would use when you want to solve a momentum equation, for example, or any other transport equation. You need to preserve the sharpness of alpha, but also the boundedness of alpha. These are two big requirements. Now, the geometric VOF, the one that Basilisk has implemented and the one that is also implemented in the inter-iso advector, in a nutshell, it finds a linear approximation of the interface in a cell cut by the interface. And once this linear approximation is found, I'm not going to go into the details of this integral, but it's simply calculating how much of the volume of fluid from the neighbor cells to the one I'm solving for, how much of their volume will enter my cell or leave my cell. So it turns the alpha equation, or at least, let's say, it turns the convective term into a geometrical problem where it will find from all these trapezoids that are your reconstructed volume of fluid, it finds how much of those trapezoids are leaving or coming into the cell. So it turns the convective term actually in a geometrical calculation of the volumes of fluid. This ensures mass conservation if it's done in the right way. So you get, if you have an initial droplet moving in a domain and deforming, at time 0 and at time infinite, you can quite say that the volume of the droplet is, the mass of the droplet is preserved. It comes at a large computational cost because doing all these calculation of volumes going across cells, it takes time. It takes time and it becomes very complicated if you have a non-orthogonal mesh. But remember that OpenFOAM is designed to be used by industries. So it is done to work with any kind of mesh architecture. So they had to do something. The first VOF implemented in OpenFOAM was algebraic. So it uses the typical interpolations on a phase center. So it doesn't use any geometrical reconstruction. But then it uses this anti-diffusion term here. This anti-diffusion term, you can imagine as making a tiny mountain of sand at the beach. The sand will fall off, and with your hands you keep bringing the sand back to the mountain so that it stays at the same altitude. So in a very descriptive way, this anti-diffusion term imposes a flux inward to the cell to counteract the spreading of alpha. And there is a lot to say here. This has been going on for 20 years, the improvement of this algorithm. Essentially, it looks at the interface orientation and it tries to find the right discretization. It corrects the discretization scheme to make sure that alpha remains bounded and sharp, but without changing the dynamics of the flow. So OpenFOAM has been developing this scheme forever, and it's been implemented there ever since. And it needs some tuning, so you may need to tune this coefficient C alpha, which tunes the interface compression. So top right here, you see a rising bubble in a pool of liquid, and with no anti-diffusion term, you see that the alpha 0.5 line, which is the black line, it's still there, but you have all this diffusion of alpha around it. So this is without anti-diffusion term. With the diffusion term, the situation gets much better. Also refining the mesh, the situation gets much better. Here we have a film. It's a film of liquid that is sheared by an airflow upward along this inclined surface. With low compression, you see that the white line is the alpha 0.5 line, so is the interface. But the field of alpha is very much diffused across the interface. Increasing this factor, you get a much sharper volume of fluid field across the interface. Yes? So usually I define the interface as that line where alpha is equal to 0.5. It's an isocontour line, 0.5. It may not be the exact location of the interface. If you use, for example, a piecewise linear reconstruction of the interface, it may not be exactly on the same line. But bear in mind that with the algebraic method, you don't have a piecewise linear reconstruction of the interface. You don't have this actual line with this methodology. Any other question? Please feel free to ask, because it's very good to, to respond in real time and to deepen the discussion where it's needed. So, advantages: low computational cost, because this is just interpolations. There is no interface reconstruction to do. It's very, very simple. On the other hand, mass conservation is not ensured. So OpenFOAM has some specific techniques to make sure that then mass is conserved. And when you increase the sharpness of the interface, you get a worse representation of surface tension. This is because the native version of OpenFOAM is not really great with surface tension, and we'll come to this problem later on. I didn't specify here, when I was talking about geometrical advection, that Since 2016, in OpenFOAM, there is this solver called InterIsoFOAM that performs a geometrical reconstruction of the interface. It's a bit slower than the algebraic one, maybe 30–40% slower, but it's a geometric solver. If you have solvers where you have, for example, a high shear between the phases, this works much better. So it's called InterIsoFOAM and is available in the version of OpenFOAM of ESI distribution. Now, surface tension force is a big issue with WOF, and it remains a big issue with OpenFOAM depending on the kind of flow you want to study. So, surface tension force enters in the momentum equation. Typically, the surface tension force is formulated using the continuum surface force method, and here I have also Marangoni effect, but disregard the surface gradient of sigma. Let's assume that we have no surface tension gradient effect. With the continuum surface force method, you calculate your surface tension as the product of surface tension coefficient, it's a constant, curvature of the interface, this must be reconstructed locally in every cell of the interface, normal to the interface. The normal vector needs also to be reconstructed cell by cell. Everything is multiplied. Here there are like expressions to calculate normal and curvature. These are the, let's say, the original WOF expressions when the WOF method was invented decades ago. So you can calculate normal and curvature only based on derivatives of alpha in principle. And this is what in the WOF method has been done since 1984 when this method was, let's say, suggested. Then you have this norm of the gradient of alpha, which essentially locates the interface cells. So the gradient of alpha is non-zero only at the interface. Norm of the gradient of alpha, you can interpret it as a interface area density. It has the unit of 1/meter, and it's like your meter square of interface area divided by meter cube of the cell volume. Now, K equal to this thing is the big issue with the standard WOF. If you use the standard WOF where the curvature is calculated based on derivatives of alpha, so this is a circular interface with a volume fraction field calculated with MATLAB. So I've done this with MATLAB. So I have a circle. I calculate the proportion cell by cell of fluid 1 over the volume of the cell. We have 1 within the circle, 0 outside, and some values in between in the cells cut by the interface. So I know exactly this is a circle. I know exactly the curvature of this circle. The curvature should be 200. But when I calculate the curvature using this method with the gradients of alpha, you see that the curvature, you would like it to be 200 everywhere possibly in all the cells. But actually, look at the scales here. It goes from -600 to +800. So in the cells that are cut by the interface, we are in the green region, so green-yellow. So we are between 200 and 400. There's a big difference. It's a factor of 2, 400. But you have also these other cells farther from the circular interface where the norm of the gradient of alpha is still non-zero. So you need the surface tension calculated there. But the surface tension is totally nonsense. You get -600 here, +800 inside. So what happens here? In an ideal case, when you run your simulation, this is a Young Laplace problem. Nothing should happen. If there is no gravity, if there is no external flow, your circular interface should remain there forever, never moving. And if you use Basilisk to solve this problem, that's more or less what is happening, because Basilisk is fantastic in calculating all these terms. But if you use OpenFOAM out of the box, if you use ANSYS Fluent out of the box, what happens is that you see all these mad velocities being created, which are very large. They are, of meter per second magnitude. This is happening because of all these errors in the curvature. Imagine that you're feeding your momentum equation with many mistakes here, so you're imposing an external force in the flow at the interface. So, if you don't do things right, these spurious velocity fields may kill your simulation. They may not be a problem. If you have a problem where the Weber number of the flow is very large, so surface tension doesn't play a big role, you may get away with it. If you have a very large scale flow, for example, you're using OpenFOAM to study ocean waves, it may not be a problem. But if you want to study microfluidics, if you want to study, jets, droplets, bubbles, then you need to do something about it, because these velocities, they scale as 1 over the capillary number, or 1 over the Weber number. So there are some easy remedies to do this, and a simple remedy, for example, is to have a smoothing of the volume fraction field. So this problem happens because alpha is changing sharply between 0 and 1, between 1 and 0. The typical finite differences discretization scheme to calculate a gradient, they are not done for sharply varying fields. They are done for continuously varying fields, all the various finite differences method. So, because you are trying to discretize the gradient of alpha with a method which is not done for sharply changing fields, then you get a big error in the gradient. You get a big error in the gradient, you get a big error on the divergence of the gradient, you get a big error in the curvature. So, one easy solution is to smoothen alpha, and there are many ways to do this. You can smoothen alpha so that it is less sharp at the interface, but you do it only by defining a new alpha tilde where you smoothen the field and you use alpha tilde to calculate your curvature. You don't use the smoothen alpha to advect the interface, because then it would be a mess. That's actually the opposite of what you want. You use smoothening only for the surface tension. Now, this brings down your spurious velocity by 1 order of magnitude, so by a factor 10. Is not great, but it's better than not having it at all. Now, this is not the end of the world. There is a new library released for OpenFOAM, which is called two-phase flow, which is fully available on GitHub. You can install it in the virtual machine I have provided. It goes plug and play. And it has all the more sophisticated way to calculate surface tension, including a level set function, a parabolic reconstruction, the height function method that Basilisk has inside. Not only, it includes a lot of methods to calculate phase change. So I would call this one the ultimate library for OpenFOAM, which is not in the official release, is available on GitHub, and is a fantastic library to do two-phase flows. There are also some publications where they compared Basilisk to this library here for the typical case of a bubble rising in a fluid, in a case where you have a low viscosity fluid and the bubble rises, making some helix, and it can achieve the same results as Basilisk. A bit slower because there is no balancing being implemented, but it could be a good alternative. Radu.
Out of curiosity, there's a lot known about how the functionality works in the context of also the solid surface because it's a triple contact.
Yeah.
Does it do contact length reasonably well?
So OpenFOAM by default has a static contact angle formulation. So it works well in the sense that it's robust.
Yeah.
Then if it's realistic or not, I guess it depends on the problem.
Yeah, because in Basilisk that is something that's a very new sort of bleeding edge type of functionality.
I remember that there was no solid boundaries in the past.
Yeah, for embedded geometry.
Okay.
If it's a boundary of the domain of the square domain, it's usually fine.
Yeah.
An embedded boundary, I think the recent contribution came in only 2 months ago.
Oh, wow,
So it's
okay.
really new.
Okay.
But it's an interesting kind of
Yeah, absolutely. Let's say in OpenFOAM, contact lines are naturally handled independently of the domain shape, independently of the mesh. But by default, in the WOF method, there is only a static contact angle. So it would not change over time. You cannot implement the effect of a moving contact line. But it's there, and actually, on GitHub, you can also find many libraries with dynamic contact angle. Actually, the two-phase flow library has all the Cox-Voinov, has all the possible formulations for dynamic contact angle. So this is a very powerful library to try out.
Is this in your link, in your book?
It's not in my virtual box, but it's very simple to import. You just go git clone with the name of the library, you enter in it, all wmake, and it will just compile it. It takes half an hour to compile it. I can help you out later. There is a trick in GitHub to make sure you are downloading the version of the library for OpenFOAM 2106. I can help you with that. Okay, we are, I think, 4 minutes from the break. The only thing I would do now is the start of the tutorial we will do in the afternoon. The start in the sense just copying the folder. So for the tutorial for this first part, we are going to use an existing tutorial in OpenFOAM. And you should be able to simply copy-paste this line. Let me see if it works. I'm going to go in a shell, and I'm going to go under OpenFOAM user run just to keep everything tidy. Let me see if I can copy paste. It seems to be working. So cp-r, copy the folder, $foam tutorials, it will go in the installation folder in the tutorial folder. And this is just the path to the tutorial I'm extracting. So this way, it should be just copied. I think the problem is the hyphen, maybe. Or no, it says that the directory doesn't exist. No, now it's fine. I think the problem was that by copy-pasting from the slide, the hyphen was not copied properly. So now, next to OF training, I have dam break. So dam break is that tutorial I'm talking about of the fall of a dam. And these are the folders of OpenFOAM I was talking about before. There is a folder called 0.orig, constant, system. All clean and all run are files that are created to make everything running with one single click. So if I open vi all run, if you do /all-run from within the folder, it will execute all these commands and run the simulation without executing them one by one. But during the tutorial, I would like to make them one by one so that we see all the various steps.